Okay, welcome. Thank you. I'm Mark Norris, Chair of the Safety and Reliability Group at the IMechE. Welcome aboard. Bit of domestics first. Fire procedure. If you hear the alarm, which is a continuous bell, make your way to the illuminated fire exits. Okay. Leave the building by the main front doors. Turn left along the pavement without crossing the road. Pass beyond the end of the building and wait on the wide pavement for further instructions. Fire stewards will be on hand to help with the evacuation. Don't come back in until someone says it's okay. There are no fire drills due to take place. Now I can introduce the speakers. We have Keith Miller from Wave. Keith has over 35 years of experience as a safety engineer, making some highly innovative changes within the oil and gas industry. Although once a so-called QRA expert, he grew to understand how deceptive these models are and wrote an award-winning paper debunking them technically, mathematically, and legally. He firmly believes that a paradigm shift is necessary in safety engineering and now promotes scientific method and the well-reasoned argument. He now sits on the IMechE Safety and Reliability Working Group 2 and is author of their publication ALARP for Engineers, a technical safety guide, which is intended to be a more rigorous, systematic and legally compliant means of meeting our safety and legal obligations. Unafraid to challenge authority and myths, he had become one of the most controversial and interesting speakers on the conference circuit. With Keith is Steve Hillier, Director of Asset Management at Worley. Steve is a fellow of the IMechE and has been part of the IMechE Safety and Reliability Group for a number of years. After graduating, Steve spent some time in aerospace and then moved into the energy sector. Steve has over 15 years' experience in asset management in a variety of sectors, including gas power generation, offshore energy, and gas distribution, focusing on integrity and asset risk management. Steve is now Director of Asset Management at Worley. We now have a presentation, which will be why we needed new guidance on ALARP, why risk cannot be quantified, and how to undertake a legally compliant risk assessment.
So this is a bit of a dual act between myself and Keith. So I'll start, then Keith will set and then I'll close. So ALARP is a concept that's enshrined in UK legislation. It's very simple, but can be we found this application will be challenging. Given its importance, the Safety and Reliability Group considered necessary to produce a guidance document that provides members and other engineers a basis for robust decisions and ALARP arguments. So what we're going to go through today, we're not going to go through the document in lots and lots of detail. This is about the story, I guess, of why we decided what was necessary. Some of the key points in the documents, some of our reflections and the next steps. So in terms of background, the Working Group 2 hold an annual ALARP seminar. This is always really well attended. I think we generally get more than 100 people attending that seminar. Lots of good discussions, lots of different perspectives from different industries. It's clearly a topic of interest. And this has sort of shown us that although ALARP is a simple and decades-old concept, it is hard to implement and it generates a lot of debate. Furthermore, there's no specific mandatory qualifications, and most engineers are exposed to ALARP at some stage and require guidance. We also recognise there's a lot of ambiguity and misinterpretation around the legal obligations under ALARP. So that's sort of setting the scene, I guess. And then we've then had some more specific concerns as a group. The first one was saying there is that what we saw was a lot of people actually picking numbers, chucking them at the carrot diagram or 5x5 matrix.
So sorry.
Yeah, so we had a few specific concerns. One was the feeling that a lot of engineers were picking numbers, throwing them at the carrot diagram or 5x5 matrix, and considering that to be a sufficient amount of work to demonstrate ALARP, with not really sufficient understanding of the numbers or whether consider control measures. Yeah, secondly, an increasing concern that some substantiated qualitative assessments were prevalent, and they were being used inappropriately to manage risks. We also, during our seminars, we've identified that a lot of high hazard industries had established frameworks, but a lot of engineers operate outside those frameworks and are still managing significant risks. And I think as a group, we were concerned that the IMechE members may be exposed here and maybe not adequately supported. That was really, I guess, the reason that we felt it was necessary to produce a guidance document that critically placed the technical requirements within the legal context. So what I'm describing here is the timeline. You can see we've got a year of 2018 there. That was the time that, as a group, we considered it necessary to effectively support the members through some document. There's a bit of discussion within the group. 2019, we then produced the project charter, setting out the scope, objectives, the target audience, and the way we were going to consult on the document. At that point, we were planning to produce an industry agnostic guidance document for practitioners, and we expected to take 12 months. And you can see it didn't quite take 12 months. It took a bit longer for reasons we'll go into. But when we produced the first draft, we in line with the charter, we gave the wide range of stakeholders, and we felt it was really important to consult with legal professionals, safety assurance professionals, with the working group, review the document, the board review the document, statisticians as well. So we were really keen that we got a wide range of input into the document. That was really insightful. You know, what we saw was a lot of opposing opinions from stakeholders. It's clearly a very emotive subject, and we found that specifically on the area of QRA, there was lots of different opposing opinions about the use of QRA. So as a group, we took the view that we needed to present a balanced position and express pitfalls for different techniques and different tools, and really critically in the area of risk prediction. 2021, we released the document. There was significant interest in the high number of downloads on the website, and we're now currently working through revision 2, and you can see there it says future ongoing updates and improvements. I think we see this now as being something this live document. It should always be used to sort of provoke thought and record best practice at any given point in time. So that's the timeline. I think I'll hand over to Keith now, and you'll go through some of the contents of the document and some of the key principles.
Thanks, Steve. So the document, you see here the contents, some sections that we thought really important. For instance, section 2, where we've covered safety legislation, and we've taken a lot from case law in order to give you examples of how the law works and kind of decisions the courts will make. That's an important section. We then go through a brief introduction to the risk management processes, how to identify risks, comprehensive lists of guide words and so on, process, then evaluating how to reduce consequences. One of the basic or simplest approaches to safety management is to reduce the consequences if you can. So we've got that first. Section 6, the analysis, talks about all the different tools, things such as FMEA, HAZOP, STPA, safety critical task analysis, and so on, listing the kind of pros and cons, strengths and weaknesses of each of those different tools. We then talk about life cycle criteria, which this is cross-fertilization from other industries. This is taken very much from process safety, which is used in the process industries. And we've taken those principles because effectively they apply across the board, and they are the sort of things that you may need to consider in any industry. Then finally, how to produce and present your case for safety, which may be a legally required document in some cases, and the upkeep of that with time after once you've got that accepted and you continue with your processes. We've listed a lot of the common pitfalls, and then in the appendices we have put quite a bit of detail into the problems with risk prediction and risk models, and finally a sort of compliance checklist, which is a handy checklist to go through. So I'm going to talk now about sort of three things, really. I want to talk about some basic principles that I think people need to understand on this sort of risk prediction area, and then take it through to a solution to that, which we're proposing, which is what we call the proportionality matrix, which I'll explain, and also the well-reasoned argument, which is one of the strong points of this document. So there are a few basic principles which are important to understand. And this first one, that accidents only happen due to unknowns, and risks only exist because of these unknowns. If you know everything about a system, if your knowledge is 100%, you would be able to foresee what the system will do and what the outcome would be, whether it would fail or succeed. But because we don't know all of those things, and any socio-technical system is too complex to know all of those details, then there will be unknowns, and therefore there will be risks. The problem that we have is that this creates a paradox, that if you want to calculate or estimate these risks, you need to know the unknowns. It's the old Donald Rumsfeld's unknown unknowns, and you can't quantify what you don't know. This is a kind of umbrella statement, and I think it should be reasonably well understood by most people, and it explains why you will struggle to build any kind of model that would be credible. The second one is that risks varies with knowledge, and it tends towards certainty as your knowledge increases to total knowledge. So ultimately, there is no fixed risk. There is no correct risk or wrong risk. Risk is a function of both the system and your knowledge of the system. So if you quote a risk, you really need to quote what your knowledge is in order to come to that conclusion. The third one is that accidents are very rarely random events, but attributing a probability implies randomness. And if something's random, that implies that you can't control it. A coin flip is random simply because no one is capable of flicking it accurately enough to get a head or a tail. So we regard it as random. But in reality, when you read accident reports, you find they're fairly thick documents that highlight numerous aspects to that accident that we could have known about and probably should have known about. And therefore, you can't treat that as a random thing. Fourthly, accidents exhibit chaotic characteristics. And what this means is that it's a bit like the butterfly principle, where if you change, there may be many variables in a socio-technical system which lead to the risks. And if you slightly adjust one of those variables, you can have an enormous effect on the risk. We know this from looking at accidents such as, take Piper Alpha, for instance, where the problem was a subtle factor in communications because of perhaps a poor permit to work or handover process. And also due to the fact that the relief valve wasn't on the skid, it was actually in the roof. So it looked as though everything was okay and the accident happened. You can't model those things. They're too subtle. And so what this does, it means that any predictive model will inevitably underestimate the risks in a high-risk system. And finally, low risks should never be dismissed, because accidents generally only happen because someone thinks the risk is low. It's difficult to find an accident where that wasn't the case. So with all of these things in mind, what we needed to do was to try and produce a more deterministic approach to dealing with your hazards and demonstrating ALARP. And what came out of, sorry, I'm jumping ahead. I missed, I've got this one. So there are one or two more key messages that come out of this. So humans cannot assess the probability of events. We're good at developing heuristics. Heuristics are rules that help us get through life. So, you know, if we go back to the hunter-gatherer aspects of our lives, we figured out certain rules, like stay downwind of our predators, then we don't get eaten. We don't know what the probability is that we get eaten. We couldn't say whether it's 30, 45 or 73%, but it's a rule. And this is whether you're cleaning windows and climbing a ladder, whatever you're doing, it's easy to think you can assess risks. And yes, you can tell the plausibility of what you're doing, that if you put it on unstable ground, then it's credible that that ladder is going to slip and you'll fall off. But you can't put a number to it. And one of the problems is that as engineers, we use sound engineering judgment regularly. But we need to recognize that sound engineering judgment relates to deterministic aspects. So if I have a pump, I can generally look at a pump and say whether it's big enough for what I want it to do. If it's 10 times bigger or 10 times smaller, I would recognize that and easily pick it up. Same with a beam on a bridge or something. Many of this kind of problems that we have can be generally assessed within an order of magnitude, and that's what we call sound engineering judgment. But it doesn't relate to probabilistic analysis, especially when we're talking about rare events. We can be orders of magnitude out and we would have no idea. And especially because you cannot verify any of these predictions. You know, if you're saying that a nuclear power plant will blow up once in every million years, you'll never be able to say you're right or wrong. The fact that we've already had Fukushima, 3 Mile Island, Chernobyl, wind scale, you'd be a fool not to be a bit suspicious. We have plenty of tools, and it's really important that we understand and challenge these tools. And also the fact that ALARP is not a standalone thing. It's not fixed, and our risk will change with time. And we need to understand what it is, change processes, changes in the environment, changes in activities, and so on, so forth. But ultimately, the question is one of reasonable practicability. Those key elements of ALARP. What is reasonably practical? How much effort should we go to determine whether our risks are alarmed? So what we've done is we've produced this thing called the proportionality matrix, which does away with the subjectivity and the ambiguity of risk matrices. And it uses the worst reasonably foreseeable consequences to determine the level of analysis. And I say the worst reasonably foreseeable because foreseeable is a term from case law. The courts tend to look at what's foreseeable. If they judge something to be unforeseeable, you'll generally not be held liable for it. But some things, most things are foreseeable, and generally the courts, what we hear of all the time is the courts saying, yes, that was foreseeable, therefore you've failed in your legal obligations. So we can split that down into just three levels, basically injury, a single fatality, or multiple fatalities. And for each of those, we can then start to define what sort of level of analysis we would do. So at a basic level, we might identify the hazard sources, what we're dealing with, apply good practice and standards and so on, as you would expect. But as we move to more serious consequences, we would not need to start thinking about identifying initiating mechanisms, failure modes, barrier flaws, and ultimately with multiple fatalities, you're going to have to start thinking about what the causes are, human factors, design error, so on and so forth. So imagine we do a HAZOP and we find 100 actions. Typically, people will use a risk matrix to rank all of those actions and then determine which ones they're going to either undertake at all or which ones would be the most urgent. But as we say, the risk matrix is not effective because a lot of things can easily be put into the green area and dismissed when they should perhaps be somewhere else. And I'm sure we've all seen people put something in a risk matrix and then someone else changes it. The point here is we could apply this to our 100 action items. What ALARP says is that everything needs to be alarmed. That's what the law says. It doesn't say that you can forget certain things. And this gives you guidance. So it tells you exactly what you need to do for any particular level. I will just say this is a development. The one you'll see in the existing one is slightly different to this. This is, I think, is clearer than the previous. So this will go into our next revision. So it's one of the key deliverables. So the final thing I want to talk about is the well-reasoned argument. And basically, both the proportionality matrix and the well-reasoned argument are in here because they are legally defendable and the sort of things that a court will want to see. So it's a much more intelligent way of evaluating your risks. Basically, in the document, we've given you ideas of what you should be looking for. I don't intend for you to read all of those pointers, but it gives you an idea that shows you the kind of things that we need to think about there. And as a kind of checklist to make sure we've developed something that ultimately, should the worst happen, we may have to defend it in court. And that should give you a good chance of demonstrating that you've met your legal obligations. So I'll hand back to Steve to give some reflection on that.
Yeah, so just picked a few of the key points in the document there. But it's a lot bigger than that. I mean, I think I mentioned we had this project charter at the start, and I think our expectation was this would be around 50 pages. I think it's everyone had a, yeah, so it turned into quite a big, meaty document actually. And I think there's a couple of points here. I mean, I think we understand it to be the most downloaded IMechE document. I think it just shows what a level of interest there is in this topic. It's sort of not broad. It's about, I think it's quite broad and comprehensive. The idea is it covers lots of sectors. It goes from case law right through to the detail of how to use different tools. I think some of the feedback is it's been some of the pitfalls and concerns that we highlight are useful when people are trying to grapple with bow ties and FMEAs and things and QRAs. But what the objective we set out was to provide something that was deterministic and legally compliant solution. And Keith's taken you through a couple of things there regarding the proportionality matrix and the one reason argument. But we see this as being a vehicle for continuous improvement. We don't see the document as it stands today being a version that will sit there now for the next 10 years on the shelf. It's something that we should be using now to continuously challenge thinking, challenge methodologies, and record best practice. And I think just touching on the future, I mean, one of the debates we're having currently in the working group is how does this deal with the future of an increasing complex world of systems and data? They clearly require more rigorous and systematic and scientific analytic processes. And AI, obviously talks about continuously at the moment. And the implications of that in safety engineering needs to be understood and considered. I think one of the things that will bring is decisions made within models that we don't understand. So that clearly has been dealt with from an ALARP perspective. But I think our view is that the concept of well-reasoned argument will become even more important going forwards because it needs to underpin the more sophisticated technology we're using as engineers. So in terms of key takeaways, this is actually our slides. I think we're quite good for time, Mark. But in terms of the key takeaways, we recognise that ALARP is not an easy concept to work with. And through the process, I think that's been reinforced. But it's important to support the IMechE members with documentation guidance and also documents that give people the sort of things to think about. And I think that's what one of the key things this document is giving people the opportunity to think about things differently potentially. Opinions about ALARP vary, but we should always strive to make analysis rigorous, systematic, scientific, and legally compliant. I think the third point there, I think, is really important. We think it's very, very it's essential. We're critically questioning and challenging methodology all the time. I think as soon as we start closing our minds to different ways of doing things, it's inevitable there'll be issues. And I think finally, from an IMechE perspective, it's really important for the IMechE to use its position and experience to lead issues like this. I think we've there's been a lot of focus on this document, and I think it's IMechE's in a great place actually to drive these initiatives forwards. So that's it for the presentation, Mark. Yes, thanks for. I think we've got some questions now. Is that the plan?
Online as well. Any questions? Yeah, that's supposed to be
That's good, very good.
Yeah, that's it there. Hopefully we can hear. Right.
Yeah, turn that round.
That's decided to connect itself again. But fine. Fine technology. Please go ahead. And you are?
I'm quite rough on the chief engineer for the was chief engineer for the NHS in England, and now what sort of movement. Health services, there's always been built for fire, and it's got a reasonably good fire safety record. Although people do tend to like walking in hospitals to set fire to it. there's very little you can actually do about accessing the money. Since Grenfell, it's virtually impossible to get anybody to really give you sort of a quality design views and sort of, everybody wants certainty and the world wants certainty. So one of the things we've looked to do is we've tried to look to do safety cases, because I mean we've recently had a large acute hospital not that far away from us that spent 34 million on fire because of it, the group because of people's concerns. It hasn't really achieved what it set out to achieve, and it's virtually bankrupt the trust. It's taken money away from patient care. So we're very much sort of advocating safety cases to look through things, and it's kind of same safety and reliability. It's from a slightly different angle. It's about getting it to as low as we reasonably need to, not an ultimate to hit the standard. So what do you think be a useful model going? I mean, I like that in matrix where you sort of the NHS uses a 5-5 matrix and it doesn't suit fire. And there are lots of things it doesn't suit, but I mean, your model there was an awful lot better, because it is, it is the likelihood of it is somebody's going to get the come and set fire to my hospital, and you just cannot quantify that. But there's various measures you can sort of put in place around it. So would you see a direct application of that to sort of like a fire safety cases in healthcare? So I've rattled on for a bit, trying to set a bit of context.
Can I take this one? Yep. Yes, I mean, I worked for the oil industry, and one of the big issues for us was fire on our offshore platforms. And we had similar problems. How do you quantify fire risks? We had no way of doing it, really. But in the end, we did a major study which looked at all of those sources, potential sources of fire, and how we would address each one of them. And what we found in that case was a lot of the fire systems couldn't deal with the fires they were expected to deal with, and actually created more risks than, because it generated a lot of steam from the water. So we eventually came to the conclusion that it was more or less a case of, if you couldn't deal with it with a fire extinguisher, then you shut the platform down and you all went to the lifeboats until things were sorted out. It was an alternative philosophy, which was significant change, but it was based on a well-reasoned argument. Admittedly, it took us nearly 2 years to do that study, to go through all our fire cases and to understand what we were dealing with and where it was beneficial and where, frankly, it couldn't do much for us. And that means going down to the level of literally asking, how people will perish in a fire, suffer, and so on, and how people would escape, so on and so forth. So it was a deterministic analysis that actually justified removing fire pumps from our platforms, because, in the end, the fire pump was generating a lot of maintenance, which meant that you put more people on the platform, which increased the risk. So there was a case, and you can make that case. And so I'm not, suggesting that the same conclusions would apply to you, but a similar approach, like step by step going through what are the flammable materials in a hospital, what can catch fire, how would you deal with that? Would a manual approach be your best approach with fire extinguishers or whatever? Or is it such that that thing can escalate rapidly, like a Grenfell Tower, for instance, and then you, obviously in a hospital, would be in a very serious situation, I guess. So yes, that's the kind of approach that I would recommend.
I mean, the sort of correlation of that, and it's one of the things that came in, because again, this trust was facing a prohibition notice, and the bulk of everything around hospital design is about life safety. It's about the regulatory reform order.
Yeah.
So you base on safety, and you sort of you take it out, and when it couldn't be done with a reasonable timescale, the trust went to a huge length to demonstrate that if what was there more risk to the people in there of fire or losing 350 beds in this particular borough, which was a very penurious borough, and the health impacts that would have.
Mhm.
And they sort of, they went through to it. And then as we've gone, and they won the day, and the LFB were very generous and strict, but sensible about what they did.
Yeah. Yeah.
But it then sort of got back to me and saying, so, okay, so what does happen when it burns down? And you've got nowhere to put these 350 patients that you've just safely evacuated. And they all went, ah. And you think, we don't think about asset retention, it's about life safety.
Yeah.
And it's so you then go on to another big thing that we then try to do another case where you're looking at you're maintaining your asset.
Yeah.
And it does. It's.
I think there are some elements in there of sort of statistical analysis which could apply to how many hospitals burned down, for instance.
Yeah.
I'm not familiar with any myself. So, and is your hospital an average hospital, or is it worse than other hospitals? So you may be able to take a probabilistic approach to a degree if you've got statistics, robust statistics. And you also implied, that there's a balance there between patients. What are you going to spend on your patients if you deny those? You can't buy an MRI machine because you're putting a firewater system in. How many lives are going to be lost and how many are going to be gained? That's a very difficult decision, I would suggest, because generally the law doesn't take into account, how much money you've got.
Yeah.
You can't say, I just can't afford that. It's not it's not an excuse. But maybe with a government organisation, you would have some kind of justification. I don't know.
Thank you. That's very interesting.
We have one here from Bill Hawkins, fellow of the IMechE. How do the SRG see this document being used where some elements of a plant may have been designed in accordance with safety-related control system standards?
As you're talking about outdated safety-related.
I'm guessing that's the case.
Yeah.
It's retired, so.
Yeah. It's a difficult one, isn't it?
Yeah, I don't
deal with this.
No, I guess I don't see it. The risk associated with that would just be dealt with alongside any other risk. I guess I don't see why the principles we're talking about wouldn't apply in that case. But that's not dealt with specifically. We've not got a specific sort of guidance section on that, but it's part of the picture, isn't it, in terms of risks that hazards that need to be managed. So I think in line with the other things that would be dealt with.
Yeah, I think in some ways good practice deals with this because good practice doesn't say that every time a new piece of technology comes out, you throw away all the old stuff and buy new. There are plants and installations all over the country that were designed 100 years ago sometimes, and we haven't changed them out. I think when there is specific reason that perhaps a control system has been shown to be unreliable and has caused accidents somewhere, if you look at the history in the industry and you find that that particular item is less safe than today's standard, then you probably do have to upgrade it. But I certainly wouldn't see it as a standard approach, because that would be unrealistic.
Yeah, I think it's probably Keith touched on it, the temporary nature of ALARP, the needing to maintain an ALARP argument, and I think that's probably the way it's dealt with. That you've got to constantly review your ALARP position, and that might mean some obsolete equipment needs to be replaced. But I think it's a case of making sure that you don't just do an ALARP assessment and put it on the shelf, forget about it. It's the constant checking for improvements in technology, sort of things we could practice, as Keith said.
Question from Amanda Hall, Network Rail. What guidance can you give on gross proportionality?
It's disproportionality. Yeah. Well, I would quote the Ladbroke Grove rail disaster, where they used gross disproportion to demonstrate that basically gross disproportion. You used quantified risk assessment and cost benefit analysis to demonstrate that the cost of that system would be grossly disproportionate to the risk involved. And what they were looking at was the automatic train protection system, and they decided that that would be grossly disproportionate to implement it. So they rejected it. And I think within a couple of years, Ladbroke Grove happened. They killed 33 people and 250 were seriously injured. So unfortunately, I don't think that the Cullen inquiry that looked into it did a very good job, and they pretty well accepted the calculations that were done, which I think were frankly not up to what should have been. I do not believe those models are credible. And so my view, and that is actually the only publicly available decision of that type that we can see because of that accident and the accident inquiry, where gross disproportion was used to demonstrate something and then everything went wrong. I think you have to look at the uncertainty around any model, and well, there's both uncertainty and there's errors in models. There's logical errors, and logical errors can be 9, 10 orders of magnitude out, and there have been examples of that in the law courts where expert witnesses have come up with relatively simple statements which have later been proved to be in error by 1 billion times and drawing the wrong conclusion. So, you know, it is remarkably easy to make huge errors. And because you can't verify it, because you will never know, you don't know whether these models are telling you the truth. And you know, I have to quote, you know, some simple cases where I think one that I really like is what's called the boy or girl paradox. And the question is, you meet a woman, she has 2 children, one of which is a girl. What's the probability that the other one's a girl? I think most people, well, I've tested this, tested it in a previous webinar, and 54 people said, well, 50%. It's not, it's 1/3. And it's because of a logical error that's in the way that you calculate that figure. And we've seen similar things like the Monty Hall problem. You may have familiar with the Monty Hall, where he has 3 doors, one's got a car behind it and 2's got goats behind it. And even professors of mathematics have virtually had to resign because they couldn't figure it out, you know, whether you should change the doors. And it's a relatively simple problem. But imagine you're trying to build a probabilistic model of a nuclear power plant. How many of those kind of errors you could put into it, and even the experts couldn't find them. That's my case.
Okay. James Capper from JCNA Limited. What is a good WRA? How do we decide WRA is strong? We are writing lots of them. Motorway hazard management, and find the WRA really useful.
Good.
Yeah, well, I think, I mean, the slide that Keith had sets out a series of questions. Those, I guess, the things to test it against. So I don't know if you want to just quickly, can we just flip to
Yeah,
that?
we could flip back.
Might look possible. Might. Oh yeah, but before that, can do it. So that, I mean, that's effectively there as a list of things you can test your QA against, and WRA. So is anything there that you'd call out specifically, Keith, in terms of the critical ones? When
Gosh, I can't remember.
I mean, I think the bottom one, I think, is the key, isn't it? You know, the if a risk reduction measure has been rejected, what is the justification? I think being able to answer that question really, you know, the important one. But the document sets out a few other things in addition to this as well. But I think what we haven't done has been you know, there's not a prescriptive sort of structure. What we've tried to do is say, okay, for your industry, for your context, you might want to do it in different ways, but if you can answer all these questions, then you've got a pretty good chance of having a good WRA.
Mm-hmm. Yeah.
We have one there from a gentleman who's clearly up early, from Calgary. So, are there established processes for validating the QRA? From Alan Murray, University of Calgary.
I don't know how you would validate a QRA if you're saying something would blow up once every 1,000 or million years. How could you validate it? Yeah, that is the problem. You know, most sort of statistical analyses are done on sort of marketing, things like this, where we get feedback and weather systems developed using statistics, but they're validated the next few days when you find out whether it did rain or not. So you can then feed that back into your model and develop it. And huge mistakes are made, but they get corrected because you have empirical evidence within days. With a QRA model of a nuclear power plant, you will never know. I can't see how you could validate it. And as I say, you know, the only real way is to do peer review, quality assurance, and really look at it thoroughly. But I'm not sure that you can ever guarantee that that thing is a valid model. So we've listed a number of pitfalls in the document, and I think if you look at some of those, you'd have to ask yourself, how on earth would I ever overcome this pitfall? There may be some cases. When you do something as simple as rolling a die, you can say, well, it's got 6 sides, they're symmetrical, and it's a random roll, therefore it's a 1 in 6. That's fairly straightforward. It's a logical analysis, a calculation of the probability. But as soon as you get into complex systems, the problems become infinitely more complex, and socio-technical systems infinitely more complex again. So I don't honestly think you can ever guarantee that you've got a valid model.
I mean, the way we've dealt with it is there's a section in the document that sort of sets out a hurdle that you need to get over, which in terms of, you know, the quality of data using, the representative, and so we've tried to just come in from that angle and say, well, if you're going to do one, can you satisfy these criteria? And if you can, then your QA should be robust. If you can't, then it's not robust. So we've not really we've looked at more for the input data rather than the testing it perspective.
I think there's an example I would like to give. I attended a webinar about a year ago, and it was a young woman, PhD mathematician, who was presenting models of nuclear power stations that she'd built. And I don't think I've ever seen such complex mathematics in my life. There was Markov chains, you know, Petri networks and things I've never heard of before. And there were a lot of very intelligent questions afterwards, but I simply asked her the question, could your model have predicted 3 Mile Island? She paused and she said, well, if you told me about it, I could have done. I said, yes, but that's the point, isn't it? There was a feedback loop that wasn't what we thought it was. And so it could never have predicted that risk, that meltdown, 3 Mile Island. And this is the problem. You know, these models, it comes back to my basic point that I made, my first principle, that you can't quantify an unknown. And that was the problem. But we should have known. It was possible to know that that feedback loop was not an integral loop.
The subsequent question that now we're moving into a world where machine learning, usually mislabeled as AI, is becoming more prevalent. In that learning of random events and things that have happened, could we then start to move? It wouldn't validate it, but it would narrow the window in terms of what the uncertainty was.
I suppose that I don't think it's a matter of uncertainty, because that was a problem. And if you've got a problem, if you think a system's going to work and there's actually a flaw in it, which means it won't work, then that's a deterministic problem.
Can we predict the likelihood of there being an error in it?
Well, you could possibly predict the likelihood of having to use that system to initiate that system, which was a relief valve. So, you know, but once it happened, then it became inevitable. So I'm not sure how you would do that. I don't know how artificial intelligence could tell you, unless the artificial intelligence was there checking you as you did the design. It would have had to tell the engineer, no, you've just designed a control loop that doesn't work. So that's when it should have happened, not as a safety assessment later on.
Because there's a rule of thumb about how many lines of code there are in a program. I think Space Shuttle was the only one with code that didn't actually go wrong.
Really?
Yeah. That's it.
Mm-hmm.
Everybody else has had flaws in their code. So any kind of control system that's computer controlled, guaranteed to have a flaw.
That's interesting. Yeah. Mm-hmm.
I think, I mean, ultimately, certainly went with Keith. I mean, there's a difference, I think, between using that for reliability type issues where you do have failures. Whereas I think what, you know, principally Keith's talking about are the events that don't happen very often. You know, the big accidents. And I think that's where, you know, the data is just not there because they don't happen very often. But if you're using it for some equipment that there's no real safety consequence and you accept failures, then I think there's a different use case then potentially.
Certainly with some systems where if you're doing a reliability analysis, for argument's sake, and you've got components with random failure rates, mean time between failures, which you can rely on, and you can draw a block diagram of that system, all the components, then you can build a mathematical model of that. But it does mean that you can't have any common mode failure mechanisms, for instance, and most systems do have common mode failure mechanisms, but theoretically it's possible. And I think, you know, reliability analysis is one area where some models can work acceptably.
Someone just asked how they can get a copy of your paper that was referenced in
You mean the document or?
the one that you won the award.
Oh, the one I won the award for. Yes, that's on the IMechE website, but I think you have to pay for it. No, the original paper was quantifying risk and how it all goes wrong. If you Google that, you'll find it because it's on ResearchGate, which is an open resource.
Yeah.
Mm.
Taking on the question. Saying, how do we think the guidance might be formally adopted? I don't think we're looking at it being formally adopted by anybody, are we?
No, it's not. It's not for that purpose. I mean, it's not a. It is. We thought quite heavily about the title to give it, and it's a resource that we expect people to to use as and when they need it, but it's not intended to be a prescriptive document that people sort of work through from page 1 onwards. So I'm not really sure there's I mean, what do you agree with that, Keith? There's not been.
Yeah, I think some companies have fed back to me that they've used it as the
Yeah.
basis of their safety management systems, and so that's about as formal as it can get, I guess. But I mean, it is, as you say, Steve, is guidance that we've produced. There's plenty of guidance out there. There are plenty of opinions as to what's right and wrong. There's no hard and fast rule, but I just like to think that if you follow this, you would be in a better position legally.
Asked for a link to the IMechE document. It's being revised, so that link will be added once it's been revised. Do we have any more? We've got 2 minutes. Any last questions? Or any last statements to sign off?
I could give you a nice example. We talked about space shuttles. So on, I remember when I was young and man first went to the moon, and NASA said, predicted that this guy's got a 50-50 chance of getting to the moon back safely. They actually sent 6 missions to the moon and they all came back safely. So I think, would you flip 6 heads on a coin? Not much chance, really. And then they said that they developed the space shuttle, and they said that will fail once in every 100,000 flights, and at a failure rate of 1 in every 65 flights. So it was over 1,000 times wrong. So I just think that's a good example of showing you how wrong these assessments can be.
Thank you. I see someone's posted a link to your paper, that video. So thank you, Andrea, for adding that. And we are done before we get into more questions, because we'll be here all night. And I think it's good, gentlemen, for dinner. Okay, so thank you, especially to the very large audience online.